Our last two lessons emphasize strategies that are generally useful for solving puzzles. In Lesson 2, we saw the importance of looking for creative, outside-the-box solutions to problems, and we attempted to train our minds to be open to such solutions. In Lesson 3, we learned that mathematics is not about mindless symbol manipulation, but rather is about solving the problem, whatever the problem might be. Algebra and symbol manipulation are merely useful tools in our arsenal, but sometimes applying them with too much enthusiasm can actually get in the way of problem solving. For the remainder of this course, we're going to look at other tools that mathematicians find useful for thinking clearly about puzzles, and we'll start with the most fundamental tool of them all, logic. Logic is all about thinking clearly and carefully, and good luck solving much of anything either in math or in life if you're not doing that. Let's try a warm-up puzzle. All of our puzzles in this lesson will involve an unusual island with two tribes of people. There are knights who only make true statements, and knaves who only make false statements. You cannot tell what tribe a person belongs to just from looking at her. The only way to tell who is to work out the logical consequences of their sometimes cryptic statements. Puzzles of this sort were developed to a high art by logician Raymond Smullyan, whose work we also met in the last lesson. Now, suppose you're walking on this island and you meet two people. Let's call them A and B. You ask A what types of people they are, and A replies, "Both of us are knaves." Can we conclude anything about A and B? If you want a few moments to think about this, I recommend pausing the video here. Are you ready for the solution? The key observation is that A cannot possibly be a knight. If A is a knight, then clearly they're not both knaves. This would be an instance of a knight making a false statement, which is against the rules. Therefore, it simply must be that A is a knave. What about B? Could he also be a knave? Well, if he were, then A's statement that both of them are knaves would turn out to be true. But then we would have an instance of a knave making a true statement, which is also against the rules. So the only way out of this trap is to assume that B is actually a knight, and the answer is that A is a knave and B is a knight. We got a lot of information out of A's simple-looking sentence. What we've just done is an exercise in pure logic. There was nothing to calculate and no symbols to manipulate. We just had to consider what followed from the statement that A made. And that's what logic is all about. It's the science of what follows from what. For example, let's assume for a moment that I never lie. If I truthfully tell you that my cat is always asleep at 4 o'clock in the afternoon, and then you look at an accurate clock and see that it really is 4 o'clock, then you conclude that my cat is asleep. If instead you see my cat walking around and plainly not asleep, then you conclude that it's not 4 o'clock. That's logic. Logic never really seems all that difficult in concrete situations. You show some mastery of the subject every time you search for your lost keys by retracing your steps. You say, I know I had my keys when I left the house, and then I visited locations X, Y, and Z, and I could only have left my keys at a location I visited, so I must have left the keys at one of X, Y, or Z. Now, of course, you never really pause to spell out the argument, and that's precisely the point. You process the basic logic of the situation so automatically that you're hardly aware you've reasoned at all. And it's not just that these conclusions seem very natural and obvious, it's that they seem fundamental in some way. Suppose a skeptic sincerely challenges your conclusion about my cat. He accepts that I never lie, but even so, he says, how do you know that it follows that my cat is asleep? You'd hardly know what to say. If it's not obvious that my cat is always asleep at 4 o'clock, and it is 4 o'clock, imply that my cat is asleep, then what could I possibly say to convince you? To what more readily understood principle could I direct your attention to make you understand the basic logic involved here? You'd probably just repeat the premises to the skeptic, speaking slowly and loudly, and then make a gesture that expressed your exasperation. Writing in 1881, the British philosopher and mathematician John Venn, whose name you'll recognize from his famous Venn diagrams, said, "It may almost be doubted whether any human being, provided he had received a good general education, was ever seriously baffled in any problem by what could strictly be called merely a logical difficulty. Do we ever fail to get at a conclusion when we have the data perfectly clearly before us, not from prejudice or oversight, but from sheer inability to see our way through a train of merely logical reasoning?" Indeed, the extreme naturalness of basic logic had already been remarked upon in antiquity. The ancient Roman philosopher Sextus Empiricus, commenting on prior work by a philosopher named Chrysippus, wrote, "Chrysippus declares that the dog makes use of basic logic when, on arriving at a spot where three ways meet, after smelling at the two roads by which the quarry did not pass, he rushes off at once by the third without stopping to smell. For the dog implicitly reasons thus: the animal went either by this road or by that, or by the other, but it did not go by this or that, therefore he went the other way." Apparently, logic is so simple that even dogs understand it. But try telling that to folks who write logic textbooks. Open up such a book to a random page, and you just might see something like this. This comes from the work Principia Mathematica by Bertrand Russell and Alfred North Whitehead, whose goal was to place all of mathematics on a solid logical footing. I promise there won't be a test at the end of this, but if you're wondering what all of that means, let me show you their very next sentence. From this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. Even 1 plus 1 equals 2 can be made to seem very complicated if you really want to spell out every step that's involved. For our purposes, it will be sufficient to stay in the shallow end without concerning ourselves with the very deep questions worried over by philosophers and mathematicians. Logic is not so bad in specific cases, but it does get more difficult when you try to write down precise rules as to what follows from what. So let's leave that behind for now and return to the island of knights and knaves. Remember that knights always tell the truth and knaves always lie. So what would you make of the following situation? You meet three people this time, who we shall call A, B, and C. You ask A what type he is, but his answer is just an incoherent mumble. So you ask B to tell you what A just said. He says, A said that he was a knave. At this point, C perks up and says, "Pay no attention to B, he's lying." What can you conclude about the three people? Put me on pause and see what you come up with. So, what should we make of the dialogue between A, B, and C? Well, let's focus on what B said. He said, A said that he was a knave. Do you find that credible? I don't, and here's why. No one can claim to be a knave, since a knight who said that would be lying, and a knave who said that would be telling the truth. That means B must have been lying about what A said, and therefore B is a knave. That implies C was telling the truth when he called B a liar, so C is a knight. But that's as far as we can go, however. A might have said anything in response to our query, meaning we cannot infer whether he's a knight or a knave. Okay, here's another problem. It's basically a souped-up version of our opening puzzle. You again meet three people who we still call A, B, and C. This time, A says, exactly one of us is a knave. B says, exactly two of us are knaves. And C says, all of us are knaves. What do you conclude this time? I especially like this puzzle, since I think the reasoning involved in the solution is especially elegant. So do have a go at this one before I reveal the solution. Okay, after hearing the opening puzzle, I hope that C's statement that all of them are knaves caught your attention. A knight couldn't possibly make such a statement, since he would be lying in doing so. Thus, right off the bat, we know C is a knave. But where do we go from here? This time, the key observation is that A and B are contradicting each other. that means that one must be a knight and one must be a knave. And since we already know that C is a knave, we conclude there are exactly two knaves among them. That means that B is the knight and A is a knave. Now, we want to talk a bit about logic in the abstract. In other words, rather than concern ourselves with specific assertions about how the world is, such as the earth is round, we want to be able to talk about what conclusions follow from given assumptions, regardless of the actual content of those assumptions. For that purpose, I'll use the letters P and Q to represent arbitrary statements, what philosophers would refer to as propositions. So when you hear me say P or Q in what follows, you should take those letters to represent arbitrary factual assertions. Let's pause now to think some more about logic. The word logic comes from the Greek word logos, which means word. This is an apt derivation, since logic is ultimately all about words. Now, we certainly have many different types of words. We have nouns, which we can take to represent objects, and we have verbs, which typically tell us what the nouns are doing to one another. We have adjectives to tell us more about the nouns, and we have adverbs to tell us more about the verbs. And then there are other words, whose function is to impose logical relationships among the component clauses of a complex sentence. For example, when I put the word not in front of a sentence, the role of that word is to tell me that the sentence is false. The word or has a similar function. If I say P is true or Q is true, the role of or is to tell me that at least one of P or Q is true. Words of this sort, whose role is to assert a logical relationship among parts of a sentence, are referred to as logical constants. In English, words like not, or, and if then serve as logical constants. Let's consider the last two. When I join two clauses with and, the resulting sentence is true precisely when both clauses are true individually and false under any other circumstance. So if I say, on Tuesday, I will eat dinner and go to the movies, then I am asserting both that I will eat dinner and that I will go to the movies. If Tuesday comes and goes without me having gone to the movies, then my statement was false, regardless of whether or not I ate dinner. Let's see how this might work on the island of knights and knaves. This time we meet two people, A and B. A says, I am a knight and B is a knave. B replies, that's true. What would you conclude about A and B? Pause the video to think it over. All right. A said, I am a knight and B is a knave. And B then agreed that this was true. Could A be a knight under these circumstances? I don't think so. If A is a knight, then his statement must be true. Since this is an and statement, that means both parts of the sentence must be true by themselves. And that would imply that B is a knave. But if A really has spoken truthfully in this scenario, then B's statement is true as well, which is impossible if B is a knave. It must be then that A is a knave. But then his statement is false, meaning that B's statement was false as well. So A and B are both knaves in this one. Another important logical constant is if-then. Statements using this construction are referred to as conditional statements or simply as conditionals. Such statements can be a little hard to parse. If I assert if P is true, then Q is true as well, what am I really saying? Under what circumstances should such a statement be taken to be true? One thing seems clear. If I assert if P then Q, and it turns out that P is true and Q is false, then the whole if-then statement should be treated as false. For example, if I say, if it rains, then we will go to the movies, and then it does rain, but we don't go to the movies, then my statement was false. Now suppose I assert if P then Q, but it turns out that P is false. What now? Well, in normal conversation, we would probably just say the statement is neither true nor false. Suppose I say, if it rains, then we'll go to the movies, but it doesn't rain. Was my statement true or false? I think we would just shrug and move on, saying that the statement was never tested. But logic won't allow that. In logic, we insist that every sentence must be either true or false, but not both at the same time. So we'll take the attitude that we only declare a sentence to be false if I've actually lied to you. If it doesn't rain, then regardless of whether or not we go to the movies, I did not lie to you, so we'll declare the sentence to be true. In other words, if the first part is false, then the whole sentence is true regardless of the truth or falsity of the second part. That takes some getting used to, since it implies that if 2 + 2 = 5, then the world is flat, is actually a true statement. Sometimes logic is weird. So let's review the rules. If I assert if P then Q, and P is true and Q is false, then the whole statement is false. The statement is true in any other scenario. In particular, if P is false, then we're done. The whole statement is true regardless of whether or not Q is true. Let's illustrate these ideas with some puzzles. You're once more on the island of Knights and Knaves. You come to a fork in the road, but you're not sure whether you should go left or go right to get to the city. You ask a local which way you should go. He says, if I'm a knight, then you should take the left fork to get to the city. What should you do? If you're not sure how to proceed, ask yourself carefully if a knave could have made that statement. Then ask yourself if a knight could have made that statement. If you apply the rules for conditional statements, I think you'll see there's only one possibility. Pause the video here. Okay, what do we make of the person who says, if I'm a knight, then you should take the left fork? Could a knave possibly have made that statement? Well, if the person is a knave, then he has asserted an if-then statement whose first part is false. But remember the rules we devise for conditional statements. When we say, if P then Q, and then it turns out that P is false, then the whole statement is true regardless of what we know about Q. Thus, the whole if-then statement is true in this scenario regardless of which fork leads to the city. So this would be an instance of a knave making a true statement, which is not allowed. The alternative is that the speaker is a knight. This entails that his whole statement is true. But since the first part of the if-then is true, the second part must be true as well for the whole statement to be considered true. Thus, the answer is that the speaker is a knight and that you should take the left fork. Let's try a harder puzzle involving if-then statements. This time, you attend a courtroom trial on the island of Knights and Knaves. There are two witnesses, A and B. Witness A says, if B is a knight, then the defendant is innocent. And witness B says, if A is a knave, then the defendant is innocent. Your task is to determine if the defendant is guilty. Put me on pause and give it a shot. How'd you do? We need a place to start. So let's see what happens if we assume A is a knave. In this case, his if-then statement must be false. But that's possible only when the first part is true and the second part is false. And that would imply that B really is a knight, but that the defendant is guilty. But now we have a problem. In this scenario, we have that A is a knave and B is a knight. So B's if-then statement must be true, and the first part of his statement is true. And that's possible only if the second part is true as well, which implies the defendant is innocent. Our conclusion is that if A is a knave, then the defendant must be both innocent and guilty, and that's a contradiction. This implies that A cannot be a knave. So it follows that A is a knight. In this case, the first part of B's statement is false, implying that the whole statement is true. Since B has made a true statement, we know that B is a knight, But now the situation is that A is assumed to be a knight, and the first part of his statement is true. So the only way his entire if-then statement can be true is if the defendant really is innocent. So the conclusion is that the defendant must actually be innocent. Okay, let's introduce a new wrinkle into our puzzles. Knights always try to tell the truth, and knaves always try to lie. But they can only do this if their beliefs about the world are correct. If I say 1 + 1 = 3, and I honestly believe that I'm right, then I haven't lied. So let's say that a person is sane if everything he believes to be true really is true. And let's say that a person is insane if everything he believes about the world is false. This leads to some complications. For example, a sane knight will want to tell the truth because he's a knight, and he will actually speak the truth because he's sane. On the other hand, an insane knight will want to tell the truth, but he will actually speak falsely because he's insane. With knaves, we have the reverse. A sane knave will want to lie because he's a knave, and he'll actually speak falsely because he's sane. An insane knave will want to lie, but because all of his beliefs about the world are false, he'll end up speaking truthfully after all. It would seem, then, that a sane knight and an insane knave will both speak the truth, while insane knights and sane knaves will both lie. This makes for some fun puzzles, as you can imagine. Let's see if you have the hang of this. You meet a person who says, "I am not a sane knight." What do you conclude? Take a moment to think it through. Okay, to solve this one, the key is to remember that sane knights and insane knaves both speak truthfully, while insane knights and sane knaves both speak falsely. Now, what do we conclude from "I am not a sane knight"? Well, a sane knight who said that would be speaking falsely, which is not possible. An insane knight would be speaking truthfully, which is also not possible. A sane knave who said that would be speaking truthfully, which is once again impossible. So the only possibility that works is that the speaker is an insane knave. Did you figure that one out? Incidentally, we'll encounter sane and insane people again in Lesson 6. Now, perhaps there's something bothering you about these problems. In real life, no one always lies or always tells the truth. Normal people sometimes tell the truth and, let's face it, sometimes lie. So let's refer to someone who sometimes lies and sometimes tells the truth as a normal. We now have 3 kinds of people: knights who always tell the truth, knaves who always lie, and normals who sometimes lie and sometimes tell the truth. With that setup, suppose you meet 3 people, once more named A, B, and C. We happen to know that one is a knight, one is a knave, and one is a normal. A says, "I am normal." B says, "That's true." And then C says, "I am not normal." Can you tell me the types of A, B, and C? Put me on pause to have a go at this one. So we have 3 different statements, one from a knight, one from a knave, and one from a normal. Let's focus on A. He's not a knight, since a knight would never falsely claim to be a normal. If A is normal, then B must be the knight, since his statement is true and the normal is already accounted for. That would make C the knave, which is impossible, since his statement is also true under these assumptions. So A is the knave. Since B's statement is now seen to be false, he must be the normal. And that makes C the knight. Thus, the answer is A is the knave, B is the normal, and C is the knight. Getting the hang of it? Let's try one last puzzle. For convenience, let's suppose that the knights on the island hold the highest rank. Normals are the middle rank, and knaves are the lowest rank. This time you meet 2 people, A and B. A says, "I am of lower rank than B." And B says, "That's not true." What can you tell me about A and B this time? As always, pause the video if you want to give it a try. So A said, I am of lower rank than B, and B said that's not true. This time, A can't be a knight, since knights have the highest rank and would never lie by claiming to be lower than anyone. Nor can A be a knave, since knaves have the lowest rank and would never truthfully claim to be lower than anyone else. So A is a normal. Given that, it's clear that B cannot be either a knight or a knave. If he's a knight, then his statement is false, and if he's a knave, then his statement is true. So it must be that A and B are both normal. And with that, we've reached the end of this lesson. I hope you enjoyed this first foray into the world of logic, and that you've enjoyed getting to know the residents of the island of knights and knaves. We'll have much more to say about logic in the lessons to come. See you next time.